Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits. And in this lecture, we will talk about design of clocked sequential circuits. In the previous lecture, if you recall, right, we looked at analysis of sequential circuits where we spoke about construction of state table and state diagrams in details. And in this particular lecture, right, we will talk about designing these clocked sequential circuits. Correct? So basically, there's a standard procedure for doing this. And how do we go about it is like the procedure for sequential circuit design is we have to first of all make a state table based upon the problem statement. The table should show, as we have seen, present state, input, next state, and outputs. And it may be easy to draw a state diagram first, and then we can convert that into a state table. So we might begin with a state table and a state diagram, and then we can talk about state table. So basically, we can begin with a state diagram, and based upon state diagram we can form a state table. What we do after that is we have to assign binary codes, that is 0 and 1, to all possible state. So basically if we have 4 states, we will have binary codes of 0 0 0 1 1 0 1 1, and based upon that we will need two flip-flops to implement a circuit, right? So basically number of flip-flops to implement a circuit would be log to the base 2 of n, where n is number of states of the system. So basically, let's assume that if in case we have 7 states, we will need 3 flip-flops. Correct? And now once we have a binary code assignment, now we will look that for each flip-flop and each row of the state table, we will find the flip-flop input values that will generate the next state from the present state. Right? And here we will look at something called as excitation table, which we have not seen till now. This will be something new in this lecture. We have seen about state tables, we have seen characteristics table, we have not seen excitation table. Excitation tables are opposite of characteristic table, and they help us find a flip-flop input based upon the present state and next state. Right? Once this is done, we will simplify derived equations using K-map and whichever method you want to use. And once we have simplified the equations, what we can do is we can simply build the circuit. Right? We have already seen how to draw a state diagram and state table in the previous lecture. We know how to assign possible binary states. We also know how to simplify equations using K-maps. We know how to build a circuit. The new thing in this lecture would be excitation table and then design. And the design example which we will be taking over here would be an example of sequence generator, as you would see, right? So basically, right, what we will look at into over here is let's look at what is a sequence recognizer. A sequence recognizer looks for a special bit pattern in some input, right? And a sequence recognizer can has only one input, x, right? So one of the input bit is supplied on each cycle of the clock, and depending upon number of inputs, it will require that many clock cycles to scan that entire set of sequence. This is an easy way to permit arbitrarily long input sequences. And for a sequence recognizer, if there's a one input X, there has to be one input Z, which will be either 0 or 1. Output would be 1 once a particular sequence is recognized, and it will be 0 in case the sequence is not at all recognized. For example, let's take an example. Let's assume we have inputs as 1 1 1, 0 0 1, 1 0, 1 0 0 1, 0 0 1, 1 0, and so on. Let's assume that we have to build a sequence recognizer which looks at this pattern and recognizes this sequence of 1001. If it does that, what is the output? Output would be 000. It would be 1 once it recognizes this circuit, 00, then this circuit over here, this over here. So 0001, 001, and 00. So basically it should be able to identify and recognize overlapping sequences as well, right? So our intention is to build a circuit which, if takes this as an input, produces this as an output. And if you see, this has to be done using a sequential circuit only with a memory element, because the circuit should be able to store the previous states. If we are in a state, if we are a state where one has come, the circuit should be able to remember that okay, one was encountered. If at all we got get a number zero out after one, the circuit should able to be recognized, okay, we had a state called 10. If again we get a zero state, circuit should be able to remember that okay, I have already encountered a state called 100, so that once the next one comes, the circuit is able to output a value 1. Correct? So this particular circuit, whatever we have to build to obtain this functionality, has to remember what happened in the previous clock cycles, and that's why it has to be a sequential circuit, right? So now in order to make a state table or a state diagram, we can start with a state diagram, right? So in order, if you have to build this sequence recognizer, let's assume that we have how many states we would need, right? We need to identify 1 0 0 1 1 0 1 0 0 and 1 0 0 1. So let's assume that we have four state where we designate state A as none of the pattern is observed. State B is something like we have seen the first bit 1 of the pattern. Let's assume state C is something like we have already seen the first two bits, basically 1 and 0 of the pattern. And let's assume D is a state where we say we have already seen the first three bits 1 0 0 of the pattern, right? If this is the case, what would happen? We can simply say that to begin with, system is in the state where none of the pattern is observed. After that, if 1 comes, system will move to a state B with an output 0. If 0 comes, system will move to a state C with 0 output. If again 0 comes, system will move to a state D with 0 output. And since, right, now once we have observed 100 pattern, now if 1 comes back, output has to be 1. And where we should land up the circuit? We should land up in B, because we have already seen 1 bit and we have to recognize an overlapping circuit. So we will have a circuit which will go to B, where if at all 1 comes, output would be 1. Is this clearer, right? So why we, the main point over here is D should not go back to A, because if D goes back to A, right, A is a state where none of the pattern is observed. If that's the case, we will not be able to identify the overlapping sequence. Now what happens if we are in A and we get a 0, right? We stay in the same state with 0 output. What happens if we are in B and 1 comes? We stay back in B with 0 output. What if we are in C and 1 comes? If we are in C, 1 comes, right? What would happen in case we will have 101? So basically what we will do, we will go back to a state B only, where we will say that okay, 1 has been identified, right? What happens if we are in state D and 0 comes? If we are in state D and 0 comes, state D something like our pattern would be this thing, which means that we are nowhere closer to any overlapping sequence. This is an unknown state. So from D we will directly move back to A. From D we will move back to A. 0 input, 0 output. Correct? This is a state diagram for this particular sequence recognizer. And we know that okay, if we have like one input, m inputs, we need to have 2 raised to power n outputs of each and every node, right? So for one input we need to have two outputs of each and every node, which we have already seen, two outputs of each and every node. Correct? And for and over here, right, we have how many nodes? Four nodes. If there are four nodes, this means how many flip-flops we need? We will need two flip-flops to implement this particular circuit, right? Now we already drew the state diagram, and let me do one thing. Let me draw this state diagram again over here. We had a state A, state B, state C, and state D. 1 with output 0, 0 with the output 0, 0 with the output 0, 1 with the output 1, and if at D we get a 0 input, output 0 0, correct? B 1 0, C 1 0. I hope this is clearer, right? This is something which we drew in the previous file also. Now based upon the state diagram, like let's look at state table, and we have already seen how does a state table looks like, right? And before we go into state table, right, we have to figure out like which kind of flip-flop. We already saw that we will need two flip-flops to implement this circuit. We need to decide whether we will use a D flip-flop or a JK flip-flop. Since we need to talk about excitation table also, let's use J and K flip-flop, because excitation table for J and K flip-flop is complex as compared to D flip-flop, and we will be able to understand it better if at all we use a JK flip-flop. So now once we have this to construct a state table, right, we should have a present state, we should have an input, we should have a next state, and we should have an output. So basically what we say, if my present state could be A, it could be B, it could be D, right? If my input is 0, input could be 0 1 0 1 or 0 1. My next state would be, if my input is A, output is like present state is A, input is 0, my next state is A, output is 0. Here it's B with 0, here is C with 0, here it stays in B with 0. C and 0 we move to D with an output 0. C and 1 we move to B with output 0. D and 0 we move to A with output 0. D and 1 we move to B with output 1. Correct? Now this particular table, right, this could be converted, right? We can always say let state A corresponds to 0 0, state B corresponds to 0 1, C corresponds to 1 0, and D corresponds to 1 1, right? Once we say this, and we have to draw a complete truth table, right, in terms of state table in terms of ones and zeros, we can simply say my present state is something like q1 q0, input is x, next state is q1 q0 again, and then we have an output which is z. Correct? Correct. So what was the next state? We already drew this. So next states are ABC, AB, CB, DB, AB. Correct. Now if we assign that nomenclature, it will be 0 0. This was B, this was C, this was B again. Now we had DBAB, right? D is what? 1 1, B is this, A is this, and output was 0 in all the cases, barring the last one. Correct? Now what we have done is, let's we said like, okay, we know these things, and now what we need to do is we need to know the inputs of flip-flops. We said like let's use J and K flip-flop, because we will come to know how the excitation table works, and we need two flip-flops, right? So we can have one more column called flip-flop inputs, and the flip-flop inputs would be J1, K1, J0, and K0. Correct? We already saw excitation table, the characteristics table, where we say qt plus 1 for jk is equal to jq bar plus k bar q, and we drew this characteristic table using this thing, where we said when both are 0, operation is no change, because j will 0, this will term will go off, qt plus 1 will remain equal to qt. Correct? This is a reset operation, this is a set operation, and this is a complement operation. Correct. So basically what we saw over here is depending upon the inputs and the present state, we can determine the next state. But here what we need to know is, we know the present state, we know the next state, we just need to know the set of inputs. And this is something which is achieved using excitation table. This means like what all inputs are required for your present state to move on to next state. So excitation tables will look like something this for JK flip flop. Present state, next state, what should be the input, and what is this operation called, right? So basically this will be same information which is represented by a characteristic table, but in the opposite way. So let's assume what all can be combinations: 0 0 0 1 1 0 1 1. If my present state is 0, my next state is 0, right? Basically operation is either a no change or a reset operation. No change or reset, right? What would this mean? This would mean that no change or reset, j is 0, k could be anything. K's don't care for us. Now if our present state is 0, next state is 1. Next state is 1, it means what? If next state is 1, either means it's a set, correct, or a complement, because the state is toggling. So it's either a set operation or a complement operation. So if it is a set or a complement operation, j would be 1. I don't care about k. How about 1 to 0? 1 to 0 is either a complement or a reset operation. Reset or complement. If it is a reset or complement means j could be anything, k has to be 1. How it's 1 1? If the state is 1 1, it means either it's a set state or it's a no change. Either it's a no change or set. Right? In this case, what would say if it is a no change or set? J could be anything, k has to be 0. I hope this was clearer, right? Just to be on the safer side, right? Let's do it once again. So we already know characteristic table of j and k, where we say j, k, qt plus 1 and operation. We say if j is 0, k is 0, right? This we already say qt plus 1 is equal to qt. This is 0, this is 1, this is q bar t. We call this operation as no change operation. We call this operation as reset. This is set and this is complement, right? Now this was characteristic table. We need characteristic table when we know inputs, we know the present state, and we have to determine the next state. What we will talk about now is something known as excitation table. And in excitation table, we know present state, we know next state, we need to know the inputs which will help us achieve present state from next state from the present state. So inputs are present state and next state, and basically we need to figure out what is the value of j and k, and let's call it an operation field over here. What all possible combinations could be there? 0 0 0 1 1 0 1 1. Now if my present state is 0 and the next state is 0, what all operations could be there? Either it's a no change operation, correct, or it's a reset operation. So we can say it's either a no change operation or a reset operation. If it is a no change or reset operation, it could be anything, no change or reset. What would this mean? J has to be 0, k could be either 0 or 1, it could be anything, it's a don't care. How about if my present state is 0, next state is 1? So either it's a complement 1 or it's a set state, right? It's set or complement. If it's a set or complement, my j has to be 1, k could be anything. Similarly, if our present state is 1 and next state has to be 0, it has to be either complement or it has to be reset. So it's either reset or complement. If it's a reset or complement, k has to be 1, j could be anything. Similarly, last, if the present state is 1 and next state has to be 1, it's either a no change operation or a set operation. Which means that no change or set means k has to be 0, j could be anything. Correct? This is the excitation table for J and K flip-flop, right? So since we are already spoken about excitation table, right? Let's complete excitation table for other flip-flops also, which is like basically D flip-flop and T flip-flop. For D flip-flop, right? What we can say is if we have QT plus 1, D and operation. We know characteristic equation for D flip-flop is Qt plus 1 is equal to D. It's independent of the present state. So basically, if this could be 0, 0, 0, 1, 1, 0, 1, 1, right? Basically, my Qt plus 1 depends upon D. So it simply means that if Qt plus 1 is 0, D has to be 0. If it is 1, D has to be 1. If it is 0, it has to be 0. It has to be 1. So this is what? Reset operation, set operation, reset operation, and set operation. Correct? Now similarly for T we know Qt plus 1 is equal to T XOR with Qt. Now if we have Qt plus 1, T, and we have to figure out the operation over here, right? Possible combination is 0, 0, 0, 1, 1, 0, and 1, 1. If my for my next state to be 0 and if my present state is 0, right? What has to be the value of T? T has to be 0 because if T is 1, T is or with Qt would become 1. So this has to be 0. So this state is nothing but a no change state. Correct? If my Qt has to be 1 when Qt is 0, T has to be 1. Basically, it's a complement. How about this? When Qt has to be 0, when Qt is 1, Qt plus 1 has to be 0. So basically, the XOR of T and Qt should give me 0. So this has to be 1 again. Again, this is a complement. Qt plus 1 is a no change operation over here. For state to remain same, when my Qt is 1, T has to be 0. So this is an excitation table for T flip-flop, right? I hope this is clearer. And now let's get back to our example, previous example. And we already know this is the excitation table of JK flip-flop. And I intentionally took an example of JK flip-flop because implementing a state table becomes difficult with JK flip-flop. And if we are able to do an example with JK, T and D flip-flop examples would be a cakewalk, right? Especially a D circuit. Now we know this thing. We know the present state. We know the next state. So if my present state is A and the next state has to be A, right? Basically, what we can do is now we can map our states over here. This is our A state, B state, C state, D state, right? If Qt plus 1 has to be same, what we can say is it has to be 0x, no change operation, correct? If my next state is going from 0 to 0 again, it's the same thing, 0x. It's going from 0 to 1. 0 to 1 means 1x. 0 to 0 again would mean 0x. 1 to 1 would mean x0. Here 1 to 0 would mean x1. 1 to 0, 1 to 0 would again be x1, x1. How about 0 flip-flop now? 0 and 0. Present state is 0, next state is 0, which would mean it's 0 and x. 0 to 1 would mean 1 and x. 1 to 0, correct? We are comparing next state and the present state. 1 to 0 means what? It will be x1, correct? 1 to 1 would be x0. Similarly, 0 to 1, 0 to 1, both would be 1 and x. And finally, 1 to 0 is nothing but x1 and 1 to 1 is nothing but x0. Now what we have done is we have completed our flip-flop inputs and now we can simply get equation at the input of flip-flop inputs J1, K1, J0 and K0 using a K-map as a function of present state and input. right? So basically, if I have to copy it again to the next, let's come here. Now we are continue example continued, design example continued, right? So basically, our flip-flop inputs were something like this. Let me just capture these values again so that this particular one example is clearer to all of us. These were like present state, these were input, these were next state, these were flip-flop inputs, this was output. X. Next state I will not capture because eventually we know this is a next state. Now we have to draw a output also is Z. Flip-flop inputs is J1, K1, J0, K0, right? So we know these values. This is like a normal operation 0 to 7. Here the values were 0, 1, 1, 0 and X, 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 X. Here the values were X, 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 0, 1, 1, 1, 0, 1, X, X, 1, 1, X, 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 1, 0, X, X, 1, 0. Now what we can do is we can draw a K-map. I'm just showing you one example for J1. So basically there are 8 entries, right? It's like a simple, we can have Q1, Q0X, 0, 1. This is 0, 0, 0, 1, 1, 1, 1, 0. Now what we can have is J was 0, 4, 0, 1, 2. So this corresponds to 0, 1, 2, 0, 1, 2, 3, 0. Rest all is don't care. So these are all don't cares, right? So what will be the equation for me? This one, both are essential prime implicants, both cover the circuit. So basically this implies J1 is equal to J1 is equal to this particular equation we can't put over here. So yeah, this is the best pair. So Q0 X bar, right, plus Q0 bar X. Similarly, we can arrive at an equation for K1, J0, K0 as well. If we look at an example for K0, it would be something like this. K0 would be what? K0 is 0 and 1 are don't care, 2 is 1, 3 is 0, 4 and 5 are X. So this will be this particular equation. And when we say this, in this particular things, Q1 is changing, our number would be, this is 0, 0, 0, 1, 1, 1, 1, 0. This bit is constant. So my K0 would be equal to X bar. Correct? We already know that our output Z was equal to and of everything Q0, Q1, X. Right? And similarly, we got J1, K0. And if we do a similar K-map conversions for uh, K1 and J0, we would get something like J0 would be X plus Q1, K1 would be equal to X plus Q0, right? And once we are done with this, right, we can build a circuit. We can build a circuit saying that our J and K flip-flop inputs would be something like this. We have a JK flip-flop here. This is Q, this is Q bar, this is Q bar. We have a clock. We have a clock both connected together. This is J, this is K, this is J, this is K. We can implement. For example, output Z, right? Output Z would be Q1 dot Q2 into X. This is set. So, and we know that, okay, if this is the case, This is nothing but a melee machine, and our equation was like k0 was x bar. So basically k0 was x bar. So basically what I can do is we can simply put x bar over here as an input, not of x, and then we know that j0 was equal to x plus q1. So we take x, we OR it with q1. q1 we take as an output from here. This is q1, right? This is q0. We OR both of them, we supply over here. Similarly, we will be able to build circuit for this and this, which we have already known. Hence, this is one of the example of building a circuit, building a sequence generator, a sequence recognizer where we were able to recognize overlapping sequence 1001. And to build a sequence recognizer, what we did was we started with a state diagram. We designated states. From there, we converted a state diagram into a state table. Everything was good. The new thing was we need to know the flip-flop inputs. For knowing the flip-flop inputs, once we know present state and next state, we had to construct an excitation table, and we saw excitation table for J and K was the most difficult one as compared to excitation table of D and T. Once we were done with the excitation table, we were able to complete our flip-flop inputs, and once we got our flip-flop inputs, we were able to uh, create our reduced circuit using our uh, K-map method, correct? So one thing was we already spoke about one thing which I want to quickly capture over here is we spoke about excitation tables, right? We saw this is an excitation table of JK flip-flop, and this is an excitation table of D and T. Once we notice, right, if at all given a scenario that we have to implement a circuit, it's easiest to do it using a D flip-flop, because in a D flip-flop our next state is equal to present state D, correct? If that is the case, my excitation table is easy and I don't need to go into all this excitation table of zero and don't cares, zeros and x's, and I don't need to construct everything and construct an excitation table again using a characteristic table, right? It would be easier for me to implement. But what one of the advantage of using a J and K flip-flop to build a combinational circuit is, what happens is if you say in the excitation of J and K table, there are a lot of don't cares. Since there are a lot of don't cares, right? The combinational circuit which we get at the end is a reduced one, correct? So basically, if we have to decide JK versus D flip-flops, which flip-flops should we use in case if we have to build a or design a clocked sequential circuit, right? Both of them has their own uses and disadvantage, but main point of consideration over here is J and K excitation table has loads of don't cares. If this is the case, right, we say that combinational circuit required is minimal. It's like a minimized one, right? Whereas over here, since we don't have don't care, combinational circuit is a bigger one, a larger one, larger combinational circuit. Another consideration is J and K, we need to know excitation table and characteristic table, so it becomes a bit complex to draw and analyze state tables. Over here, state tables are easier to analyze in D flip-flop. Correct? So this is one of the example I wanted to talk to you about, and actually we can see it, right? If at all we look at our previous example, if at all I have to put it right over here, in our previous example we had present state q0 and q1, let's call it ps. We had an input which was x, and we have combinations like, so basically the 2 points I mentioned over here, right, we can simply see those 2 points once we analyze these two circuits which I'm trying to build right now. Our next state we already knew in our previous example. So if you pause the video, bookmark and see it, right? You will know this is the table from the previous expression only where we implemented a JK flip-flop. Now flip-flop inputs. If I have used a D flip-flop, right? Let's call it D1, let's call it D0. If my present state is this, next state is this, right? We know that next state in D flip-flop is equal to D. So basically I can simply copy over this next state over here. So this will be 0 0 0 1 1 0 0 1 1 1 0 1 0 0 0 1. And in this case my K map would be Q1 Q0 X, right? State it would be something like 0 0 1 0 1 0 0 0, right? And my D0 would be equal to what? 0 1 0 1 1 1 0 1, right? So D1 would be equal to this and this, right? So this will not be a minimized circuit. It will be equal to Q1 Q0 bar X bar plus Q1 bar Q0 X bar, and D2 would be equal to this particular circuit 0 0 0 1 1 1 1 0, this and this. So D2 would be equal to, this is nothing but X plus this is 1 Q1 into Q0 bar, right? And anyways that remains the same, which is equal to Q0 Q1 into X. Now if we build a circuit using this, right, what all we will need? My D2 will need what? D2 will require NOT and XOR gates. My D1 will require not two notes, two ANDs and one OR. One OR. See the number of gates we end up using over here. As compared to the previous example of J and K where we were just having very simple equations, where we had like OR gate, NOT gate, and just OR gate and AND gate. So basically combinational circuit which is required in case we use a D flip-flop is much lesser, right? This is one of the comparison, right? That's about this particular lecture where we looked at the design of one of the sequential sequence generators and sequence identifiers, right? Sequence recognizer circuit. I hope you liked this lecture. Stay tuned for the following lectures as well.